Perfect. Okay, so thanks for joining UCL Radar seminar today. This talk was created by Dr. Nial Peters and delivered to the EMSIG event earlier this week. Nial, unfortunately, lost his voice, not feeling so great today, so thought I'd present this work for him. But very much Nial's slides and Nial's work that went into this. It's just a brief 10, 15-minute kind of slot presentation talking about the pros and cons of going digital and lessons learned from the ARESTOR project. The ARESTOR project is the UCL's RF system on a chip program of research that we've been completing in collaboration with Dr. Nial Peters and Dr. Colin Horn, and some further comments about that are in these slides. So we'll recap what ARESTOR is, talk about the benefits of an RF system on a chip, talk about RF system on a chip performance, then mention the comments about dealing with the data, and then summarize where we're at. So as you can see, just a brief seminar today, really. The ARESTOR system based at UCL is based on the Xilinx ZCU111 RF system on a chip evaluation board, the photograph shown here. That is the generation 1 of what they now have up to the third generation of this type of device. And there's further diversity in the types of solutions in this program platforms they've created. These are available for researchers like ourselves to purchase, but they arrive as a blank canvas with much promise to do lots of different types of activities, including communications, sensing, and a multitude of other digital solutions really based on this platform. There are reference designs, but they are fairly limited and inflexible, and inevitably, we are radar engineers and want to use it in our particular niche way that isn't necessarily mass market implementation. So we would have to start from scratch really with this work. ARESTOR, as we call it here at UCL, is not merely us purchasing a Xilinx RF system on a chip and rebranding it, repackaging it in our own box and selling it as a concept. It's really the hardware is the enabler, no doubt, and it's a step change of commercially available off-the-shelf solution. It's very impressive. But it's the red markers here, which is the FPGA configurations, the build system for FPGA configurations, and the software stack to talk to those, where the hard work and many man hours has been put in order to enable the use of this blank canvas in the way that we want to enable it. There was a paper in the EURAD Radar Conference back in April 2022 that was the first article talking about ARESTOR. And here Nial's showing the level of abstractation you have from programmable logic to Linux kernel to Linux user space to host PC and the interfaces between those. And really at a prototype RF sensor level, you want to be giving commands at that host PC level at a level of abstractation that's simple enough to set a set of parameters and a go state for your sensor. But you need to ensure that that gets interfaced down the stack all the way down to the hardware IP itself. And that's where the hard work is really. Okay, so what have we done with the sensor, with the solution? Well, we've worked on multi-band sensing of targets, looking at drone classifications of payloads at a variety of frequencies simultaneously being sensed. We've looked at joint radar and communications, where we're using what is a normal radar waveform, but index modulating it such that we're able to start putting communications out there with a traditional sensing waveform. We've looked at Internet of Things, particularly the LoRa protocol, electronic surveillance examples, where we've been able to achieve classification of LoRa signals real time on the Xilinx RF system on chip. We have some active and passive sensing concepts that we're working on and continuing to work on, which was shown at the IRS conference. We've successfully completed some multi-static trials with the system enabled by a timing and synchronization system developed by Piers Beasley. And we have a phased array project that's ongoing, hoping to move to having a multi-channel setup there. And I think this gives you the flavor of one system trying to do many things and what it's opening up for us here. And many thanks to Dylan, Murat, Annan, and of course Niall and Colin for all the enablers that we've been able to achieve these things. Great. Why RF system on a chip? Well, in your design of perhaps a 16 by 16 element setup here, you can note that if you were going to have a channelized solution being formed into eventually an FPGA at the end on the top back left-hand corner, here you would have this standard here, this JES D204, pushing the samples through what was a multi-channel ADC. And this becomes really high requirements on data rate and throughput and power. But by having a singular integrated solution, which is an RF system on a chip, there's no longer that bottleneck of that throughput there, and everything happens within a single device itself. All the ADCs, DACs, conversion, and FPGA program kind of logic are so tightly integrated, you can do it within that single block, which is a clear selling point overall. So it's more efficient energy usage is the usual given reason, but also due to the removal of need of these high-speed interfaces passing the data on. But it's more than just that interface necessarily. It also has, you need to consider any practical design. This will require most of the system on the chip subsystem. So you'll need a processor, a memory controller, and a high-speed interface. But pre-systems on a chip, these were discrete units and blocks within your setup anyway. So if someone, Xilinx in this case, has produced a very tightly integrated solution and bring them close together, it's helping you build all those things in a single fail swoop, really. And with the RF SoC, these are all tightly integrated, basically. And this diagram here shows that level of integration and all of this is within the single chip. One comment that Niall was mentioning during the EMSIG talk was that he's often asked to compare the performance, or what is the performance of the RF system on the chip that we're using. So he took a comparable device from another company in a similar area, which is the AD6688, and had a look at some specs overall from data sheets. So the ZCU111 has both transmit and receive, 8 channels each. The AD6688 only has 2 receive channels there, so it's a clear difference already. But it's able to tune to a maximum frequency of 9 gigahertz, whereas the Xilinx solution maxes out at 4 gigahertz on the generation 1 board we're using. The sample frequencies of the ADCs on these devices are 4 and 3 gigasamples per second, respectively. There is a deeper bit depth in the AD device at 14 compared to this Xilinx device. But the spurious-free dynamic range is quoted at 80 decibel carrier on the Xilinx device compared to 70. There was a point raised during the EMSIG meeting about spurious-free dynamic range, and that value, that dynamic range being quoted there, appears to be bigger than the dynamic range of just the fact of having 12 bits. So how can you have a spurious-free range bigger than the dynamic range of your bits? And the comment that was made was to do with, well, your spurious-free dynamic range is calculated after an FFT of the signals you're looking at. So you have FFT gain in there, which is adding to dynamic range capabilities, which is, I think, a useful comment to make. Crosstalk isolation, greater than 90 dBs mentioned on the spec sheet of the AD device, 70 dBs mentioned on the Xilinx device, but through measurements, we're talking about maybe 80 dBs isolation, which is good. And then costings, again, ballpark figures of what we're looking at here. There's a 2K cost for that AD solution compared to the 10K cost of the Xilinx one. No, there's only 2 channels in the AD solution. So if you needed to scale up to many channels, if that was your application, you need to stack these and purchase multiple of these. And you also need to add an FPGA board to that, which comes at a cost itself. Now, this is just one device that's making a comparison, but it gives you a flavor of where this sits amongst other digital solutions. A useful reference that was made is shown here on characterizing the performance of high-speed data converters for RF-based radio astronomy receivers. The radio astronomy community publishes quite detailed results in general on digital systems, and their dynamic range and high spec performance requirements often requires detailed analysis. So they do put out nice papers in this area and are worthwhile following. And they are particularly interested in the RF SOC as well as a solution for digitizing the signals they care about. So it goes into great detail characterizing the ADC performance of the device, and they demonstrate it's possible to get very close to the performance specified in the data sheet. Multi-tile and multi-device synchronization features heavily in our presentation in the radar conference coming up in San Antonio in a couple of months. So those details won't be presented in this paper until that conference paper is officially published. So you'll wait to see those results that we've looked at. In terms of data, Niall did some calculations here, looking at where does the data go, where can it go, how fast is this really? Okay, so we have 8 channels at 4 gigasamples per second. If you crunch numbers, that's half a terabyte a second of recording at full whack and all 8. So this is a tremendous amount of data. If you're pushing out 64 gigabits a second from the RF tile, this is all the I/O options you have and their max speeds to try and move this data down the road. Okay, and it's quite a nice visualization because it shows you your options of I/O. So 64 comes from the RF ADCs, goes into your FPGA tile. Sorry, from the RF tile into the FPGA. So what is our fastest routes off of that? Well, there is the FMC adapter option, and that can push at 49.5, I think, overall, but you're already shy of the 64 that was going in. So even with the fastest option of I/O, you won't be able to push out from the FPGA at that fastest rate. Everything else is lower than that. We've got 4 gigabytes of RAM. That's going to fill up pretty quick when you're pushing 21 to it per second. We've got these SFP28 adapters, 4 times of those, and that will get you 12.5 out. And then there's a backplane or a connection between FPGA logic to the program system, which will give you at 4 times 4.8 overall. Okay, and then from the processing side, you've got options like a larger DDR RAM space, because that side is upgradable, and we put the 32 gigabytes into it. Pardon me, but that can only come out at 10 gigasamples per sec. Ethernet 0.1, pretty piddly. M2 SATA drives or SSD drives in terms of what comes through there. So this is representing the data deluge, I think is the expression typically used for this type of industry. So how do we move this along? So clearly, key priority is to decimate, downsample, and extract just what you need at every point possible and pass it through. So what strategy do you go with? Do you kick the problem down the line, or do you data reduce? Try and use the high-speed streaming from FPGA and moves the problem downstream. It's not easy to achieve at the highest data rates possible, and you end up purchasing and acquiring further expensive hardware due to that. But if you want the absolute fastest speeds, and you want all data without any modification, downsampling, interpolation, at That's what you're going to face. That's what you're going to do. But it comes with cost and it's hard. On the other strategy could be onboard data reduction, which is a compromise between a multi-channel and a high bandwidth. Do you want N channels at lower bandwidth per channel, or do you want to use one channel and use it as wide as you can for one channel? And there was a nice paper at IRS by researchers in Warsaw Institute of Technology. They're talking about that exact trade-off. And you can run one channel at this rate, or you can run 4 at this, or 8 at that. And they showed that throughput. Maximize your FPGA processing and use other hardware accelerators like the Versal architecture potentially in the future, and stream the final data product in a way. If it's a range profile, range Doppler profile train, that's the piece that you are outputting, cut to the right Doppler and range section you care about to again minimize things. But in terms of a digital system, the RFSOC has much promise and has much flexibility. But in reality, this talk was being given to a millimeter wave radar group, sampling and creating signals at 77 gigahertz, 150 gigahertz, 220 gigahertz. You couldn't be necessarily all digital up to that degree. Here at UCL, I guess we're more typically working in sub 10 gigahertz bands, and you could create pure direct digitalization in that region. Higher frequencies and bandwidths will only compound the data problem though, and some compromises needed, and there's very much still a place in the world for analog RF front-end engineers. The RFSOC is a strong contender for digital backends because it has good data converter performance, lower power than some alternatives, and it's very complex and it has a high barrier to entry. But I think Niall's point is this isn't easy fundamentally. There isn't an easy route to do all of the things that it does. Yes, perhaps if you're designing a single device to do a single role, there is different things you can do, but building any radar, any RF sensor, any device that harnesses RF and data, it has its challenges for sure. So that was a very brief seminar on food for thought about what does a digital system really bring to the table in comparison to some other ones out there, and part of that data deluge problem. Thank you for listening, and any questions?